Lighthouse Scientific Education presents a lecture in the Molecules and Compounds series. The topic, Advanced Covalent Bonding, with multiple bonds and hybridization. Material in this lecture relies on an understanding of the previous lectures, electronic configuration, Part 1, covalent bonding, and Lewis dot structures. Before we start, it should be noted that this lecture contains material, such as hybridization, that many chemistry classes do not cover or do so to a small degree. The student should therefore verify what is expected of them regarding this material and give it the attention it warrants. Our lecture on advanced covalent bonding begins with a deeper look at what we called orbital overlap in the covalent bonding lecture. The first form of overlap that we will look at involves s orbitals, and we will use the molecule H2. For p orbital overlap, we will look at the molecule F2, and overlap involving s and p orbitals, we will use HF. A slightly different type of orbital overlap is found with double and triple bonds. The more advanced material in this lecture deals with modified orbitals and bonding. An introduction of hybridized orbitals is given, along with a procedure that outlines how to get the appropriate combination of orbitals needed for hybridization in a particular bonding pattern. And then there is the quite advanced topic of molecular orbitals, which we will only just touch on to provide some background to its terminology. All students who cover covalent bonding will benefit from a deeper description of orbital overlap in multiple bonds, and we will begin with overlap of s orbitals. To restate the definition of covalent bond, it is when atoms share one or more valence electrons. More specifically, an orbital with one electron in one atom overlaps with an orbital with one electron in another atom. The orbitals in question are the pure orbitals, or the basic orbitals, which were introduced in the quantum mechanics lecture, and they are s, p, d, and f. The simplest molecule, H2, stands in as a good example of orbital overlap involving s orbitals. Referring back to the electronic configuration of the hydrogen atom, we see that its electronic configuration is 1s1. It has one electron in the 1s orbital. Let's keep that in mind as we construct a cartoon that will demonstrate the orbital overlap. We begin with a dot diagram of a hydrogen and drawing a hydrogen atom as a sphere, with a nucleus at its center. The whole of the sphere will be the 1s orbital. The single electron will be zipping around the orbital. Now to a second hydrogen. Same construction. It also has a single electron. A covalent bond is formed when the two hydrogen atoms approach each other, merge slightly, and share the two electrons. They have become H2. The region where they merged is called the overlap, and generally it is where the two electrons are drawn. In reality, the electrons are a pair and they can be found zipping around the 1s orbital of either nucleus. Sigma bonds are formed by the overlap of ends of orbitals. A similar overlap can occur with p orbitals. F2 will nicely show this. A look at the electronic configuration of the element fluorine shows that just one of its p orbitals has a single unpaired electron. Covalent bonds are formed by the overlap of orbitals containing just one electron. A quick review shows us that there are three types of p orbitals, px, py, and pz. They are aligned along the x-y axis respectively. They are perpendicular to each other. That is, where they meet forms a right angle. While we are currently interested in the single bond with p orbitals, as a heads up, in some situations, p orbitals will also participate in double and triple bonds. More on that later. From the electronic configuration of fluorine, it can be seen that the 2pz orbital is the one that has the single unpaired electron. So we will be using that orbital to form the covalent bond. In reality, there really isn't an x, y, and z orbital. There are just three perpendicular p orbitals, and for fluorine, one of them has an unpaired electron. On to the overlap. And we start with the dot diagrams of two fluorine atoms. The single unpaired electron is highlighted as yellow. We can draw a cartoon of the two atoms like we did with H2, but to make it easier to follow, let's just draw the 2pz orbital with one electron for the fluorine atom on the left and the 2p orbital with one electron for the fluorine on the right. While we know that the electron in a p orbital is free to move about the orbital, we'll draw it as a stationary dot. A covalent bond is formed as the fluorine atoms approach and overlap their 2pz orbitals. A molecule of F2 is formed. The electrons are shown to be in the overlap of the ends of the orbitals. This is also called a sigma bond. Can there be overlap with an s and a p orbital? HF will show us that indeed a single bond can be formed between an s and p orbital. Quick note, HF is really an ionic compound, but the logic behind the orbital overlap still holds. We begin by drawing the 1s orbital of hydrogen and the 2pz orbital of fluorine. A small section of the 1s orbital overlaps with the end of the 2pz orbital. The compound HF is formed. There's a region of indicating a single or a sigma bond. Generally, this is a sufficient level of understanding bond overlap in covalent bonds. Another topic in covalent bonding is the double and triple bonds. It is important to note that all multiple bonds have a single or sigma bond, which is formed by the overlap of ends of orbitals. Of interest here are the characteristics of another type of bond, the multiple bond, as in double and or triple bond. These bonds are a way to get extra electrons around an atom to fulfill the octet rule. These are not formed by the overlap of ends of orbitals. Double and triple bonds are called pi bonds. Sigma bonds involve the overlap of ends of orbitals. Pi bonds do not. Double and triple bonds involve p orbitals. There is no hybridization, and that's a topic we'll cover later in this lecture. When they are drawn in a chemical formula, the double and triple bond are shown as lines in the same manner as the single bond. For example, O2 has a double bond, which is shown with two parallel lines. N2 has a triple bond, which is shown with three parallel lines. The molecule nitrogen will do nicely to visualize the construction of a single, double, and triple bond. A look at the electronic configuration of an atom of nitrogen shows that all three of its p orbitals have a single unpaired electron. That means that the atom nitrogen can form three covalent bonds. Let's refresh our understanding of the orientation of the three 2p orbitals. They are perpendicular to each other. Keep in mind the labels X, Y, and Z are really just there to give us some reference as to how the p orbitals are oriented in relation to each other. All multiple bonds have a sigma bond. We could choose any one of the p orbitals for our single bond. For no other reason than convention, we will start with the 2px orbital. The construction of the triple bonded N2 with a pair of 2px orbitals and their single electron as seen in the electronic configuration. A covalent bond is formed with the overlap of the ends of the 2px orbitals. As we've seen before, this is a single or sigma bond. For the chemical formula N2, the single bond is represented by a line. We're going to add a line to our cartoon to show an axis of the bonding. As we will see shortly, both the double and triple bonds are going to be parallel to this line. So far, so good. For the double bond, a second orbital with a single electron is needed. Let's bring out the 2py orbital for each nitrogen. They are placed in an orientation corresponding to where the 2px orbitals are when they form the single bond. The 2py orbital is perpendicular to the 2px orbital. And for nitrogen, the 2py orbital also has a single electron. As drawn here, the 2py orbitals form a pi bond. Unlike with a single bond, the pi bond does not have direct orbital overlap. It is a side-to-side overlap. Here, overlap means the movement of electrons outside the orbital. That is, the electron pair can cross over between the two non-touching 2p orbitals. These electrons are referred to as delocalized because they are not limited to their orbital. They can move between lobes in a direction parallel to the single bond. Remember that line we introduced to show the axis of the single bond? Here the electrons are shown to move between the lobes pictured on the top. They can also move between the lobes pictured here on the bottom, again in a manner parallel to the single bond. The double and single bond are oriented in the same direction along the axis. The double bond is still considered a covalent bond because it involves the sharing of electrons. A second line is added to the N2 to indicate the double bond. On to the triple bond and the final set of shared electrons. Another single unpaired electron is needed, and this time it belongs to the 2pz orbital. The 2pz orbital is perpendicular to the 2px orbital. It's also perpendicular to the 2py orbital. For nitrogen, each 2pz orbital has a single electron. As drawn here, the 2pz orbital form a pi bond. Again, there's no direct overlap. There is a side-to-side overlap. The pair of electrons can cross between the two non-touching orbitals. These are also delocalized electrons. They can move between the lobes in a direction parallel to the axis of the single bond. They can move as a pair between the lobes in the front or the lobes in the back. The third bond is in the same direction as the first and second bond. The third bond between the nitrogens is also a covalent bond, and as such can be added as a line in the chemical formula. 3 covalent bonds. The first is a direct overlap, and the second and third are side-to-side orbitals with delocalized electrons. That completes the basics of bonding overlap. For most students, this is as much of the lecture as they will need. For those who cover covalent bonding in a little more depth, there is hybridized orbitals. We begin with an overview. The reason we have hybridized orbitals is that electronic configurations of atoms do not always explain bonding patterns. For instance, consider the molecule methane, CH4. A look at the dot structure of methane shows a carbon to have an octet of electrons and each hydrogen to have a duet of electrons. Carbon makes 4 bonds and will need 4 atomic orbitals containing a single unpaired. However, if we take a look at the electronic configuration of carbon, 1s2, 2s2, 2p2, we see that there are only 2 of carbon's 2p orbitals with single unpaired electrons. Going strictly by its electronic configuration, carbon should only be able to make 2 bonds. It seems that the carbon's atomic electronic configuration and its bonding pattern in the dot structure are at odds. This is where hybridization comes in. Before proceeding, we should remind ourselves that an orbital is a mathematical equation that gives a region around the nucleus of an atom that has the highest probability of finding an electron or pair of electrons. It is not a large step to consider that the math behind the generation of the individual s, p, and d orbitals can be combined to form new mathematical constructs that also yield regions of high probability of finding an electron. One such combination is known as hybridized orbitals. Specifically, these are atomic orbitals that are the mix of 2 or more basic type atomic orbitals, s, p, or d. To demonstrate this mixing of orbitals, note the electronic configuration of carbon's 4 outer shell orbitals, a single s and 3 p orbitals. There are 2 electrons in the 2s and 2 single unpaired electrons in the 2p orbitals, 4 valence electrons in 4 orbitals. The mathematical reconstruction, known as hybridization, produces 4 new orbitals that replace the 4 basic orbitals. These new orbitals have an energy level between the original s and p orbitals. Since the mix is heavy with p orbitals, the energy level of the hybrid orbitals are closer to that of the original p orbitals. The new orbitals are no longer considered s or p orbitals, but a set of 4 s1p3 orbitals. We see that the new name combines the type and number of original orbitals. And as we've seen before, by convention, the number 1 is dropped. It is implied to be there. These are 4 equal energy sp3 hybridized orbitals. Referring back to the rules for generating electronic configurations, it was said that electrons are added to equal energy orbitals before pairing, which means that this paired electron in the first sp3 orbital should actually be in the 4th orbital. Push it over there. The last bit of housekeeping is to slide the 4 orbitals together. Now we have 4 orbitals that each have a single unpaired electron, which allows carbon to be able to form 4 bonds. Bottom line, hybridization provides a rationale for how an atom can recombine atomic orbitals and reassign valence electrons so that it can participate in making covalent bonds that are not consistent with its original electronic configuration. While we have that dot structure of methane, we might as well bring up a rule of thumb that relates a dot structure to a specific type of hybridization for its central atom. For most students, this is as deep as they will need to go in hybridization. To determine the number of hybridized orbitals on the central atom, count the number of single bonds around the central atom. Combine that many basic atomic orbitals into hybridized orbitals. Be sure to select the lowest energy orbitals for hybridization. Remember that these are valence electrons, so it is the lowest energy orbital in the outer shell. For example, carbon and methane makes 1, 2, 3, 4 single bonds. Carbon will need 4 hybridized orbitals. It will need to combine 1 2s and 3 2p's. Bottom line, it is the number of single bonds that gives the number of orbitals that need to be mixed in the hybridization. There are other types of hybridization that follow this rule of thumb. We will look at the most common types of hybridization from the perspective of electronic configurations. The topic of hybridized orbitals will then be summed up with a process that includes the rule of thumb given here, as well as showing us how to handle orbitals with lone pair electrons and orbitals involved in making multiple bonds. But first to the other types of hybridization, starting with the sp hybridized orbital. Examination of the term sp tells us that we mix 1s and 1p. Here's an electronic configuration that requires the mix of a single s and single p orbital if the central atoms to make 2 covalent bonds. This configuration has both electrons in the s orbital. It does not have orbitals with single unpaired electrons in them, and therefore cannot participate in covalent bonding. There are other electronic configurations that will need sp hybridization to meet the bonding pattern of the central atom. But this one, while not common, is the easiest to follow. Viewing the electronic configuration from a cartoon perspective of orbitals, a single 2s and 3 2p orbitals, we see that 2 electrons are in the spherical s orbital. They are given the form of arrows with opposite spin. Hybridization here is the mixing of a single s and a single p to form 2 sp hybridized orbitals while not changing the remaining 2p orbitals. There are 4 atomic orbitals before hybridization, 1s and 3p's, and there are 4 atomic orbitals after hybridization, 2 sps and 2p's. The 2 electrons that were in the s orbital are now separated into their own sp orbital. This new electronic configuration allows the atom to make 2 covalent bonds. The mathematical shape of the new sp orbitals is really just a combination of the original spherical s orbital and the original dumbbell-shaped p orbital. When considering covalent bonding p orbital, it is the larger lobe that contains the electron and participates in the orbital overlap of the bond. The other 2p orbitals are unchanged. Viewing all of the orbitals together in an atom, there is the first sp orbital, the second sp orbital, These hybridized orbitals are linear, with their larger lobes pointing out. Perpendicular to the sp orbital is the unoccupied py orbital, and perpendicular to that is the unoccupied pz orbital. While that makes for a busy diagram, the thing to note is that the hybridized orbitals are along the x-axis, which makes sense since it was the 2px orbital that was hybridized. A molecule that uses sp hybridization is BeF2, with beryllium as the central atom. It is a linear molecule, and the sp orbitals are the bonding orbitals. The bonds to fluorine are single or sigma bonds. The next type of hybridized orbital is the sp2 hybridized orbital. As the name implies, it is the mixing of one s and two p's. The simplest electronic configuration that can demonstrate this hybridization has 2 electrons in the s orbital and 1 in the p orbital. In this format, this atom can form one covalent bond, since it only has one orbital with a single unpaired electron. Viewed from the cartoon perspective, there are 2 electrons in the s orbital and 1 in one of the p orbitals. Hybridization occurs with the mixing of the s orbital in 2 of the p orbitals, forming 3 equal energy sp2 orbitals and leaving the final p orbital. 3 basic atomic orbitals are combined into 3 hybridized atomic orbitals. Since the sp2 orbitals are 2 parts p orbital and 1 part s orbital, the energy level of the hybridized orbitals is closer to the original p orbitals than it is to the s orbital. The 3 electrons from the configuration are added as single unpaired electrons to the 3 sp2 orbitals. Electrons are added to equal energy orbitals before pairing. The 1 unchanged p orbital is still unoccupied. The mathematical construct of the sp2 orbital has elements of the spherical s orbital and the dumbbell-shaped p orbitals. The remaining p orbital is unchanged. 3 electrons can be added to the 3 sp2 orbitals. This configuration is now capable of forming 3 covalent bonds. The 4 orbitals can be viewed together in a 3-dimensional representation. For ease of viewing, we will adjust our frame of reference so that that 2p orbital is pointing up and down. All we have really changed is the direction from which we are viewing the drawing of the combined orbitals. The drawing begins with the 3 hybridized orbitals oriented along the same 2-dimensional plane, in which the small lobes are pointed together and the larger lobes are pointed out so that they can participate in covalent bonding. That unoccupied 2p orbital is perpendicular to the plane, and we have the 3D orientation. Example of a molecule containing sp2 hybridization is BF3, with the boron containing 3 sp2 hybridized orbitals. And like the orbital overlap we saw with F2, each of these fluorines overlaps one of its 2p orbitals with an s2p hybridized orbital on the boron to make a single or a sigma bond. sp2 hybridization. On to sp3 hybridization. The simple example for this hybridization is the electronic configuration that has 4 valence electrons, with the s orbital being full and the remaining 2 electrons as single unpaired electrons in p orbitals. From the perspective of the drawn orbitals, 2 electrons will go in the s orbital and single electrons into 2 of the p orbitals. This hybridization of 1 s orbital in all 3 of the p orbitals, producing 4 equal energy sp3 orbitals. This mixing is heavy with p orbitals, so we find the energy of the sp3 orbitals to be close to that of the p orbitals. The 4 electrons of the initial electronic configuration are dispersed evenly among the 4 sp3 orbitals. The 4 sp3 orbitals share the dumbbell shape and spherical nature of the original p and s orbitals. Each will contain a single electron, and each can participate in covalent bonding. The 3-dimensional arrangement of 4 sp3 orbitals is that of a tetrahedral, with the larger lobes pointing out and capable of participating in covalent bonds. The tetrahedral arrangement will be explored further in the molecular geometry lecture. Of course, CH4 or methane is the classic example. And yes, the s orbital of each hydrogen overlaps with the sp3 orbital to form a sigma bond. sp3 hybridization. The last type of hybridized orbitals we will cover is the sp3d. Many chemistry courses do not cover hybridized orbitals with a d orbital component, so we will only briefly touch on the subject, and with just one type of hybridization. Not surprisingly, we're going to need an atom that has 3 d orbitals. Any atom that has 3 s orbitals has 3 d orbitals, even if they are unoccupied. Mathematically combining a single s orbital, 3 p orbitals, and 1 d orbital produces the 5 equal energy sp3d orbitals. Energetically, they are between the original p and the d orbitals. Also note that 4 of the 5 d orbitals are unchanged. Mixing in the d orbital creates a set of hybridized orbitals that's not too different from the sp3 hybridized orbital. And for the sake of brevity and the difficulty of showing 5 combined orbitals, we will finish the discussion of sp3d by showing a molecule, PCl5, which has a central atom that makes 5 bonds, and therefore will need 5 hybridized orbitals. The chlorines each overlap one of their 3p orbitals with one of the phosphorus's sp3d hybridized orbitals and form a single or sigma bond. Hybridization is a recalculation of atomic orbitals. It allows the atoms to have equal energy orbitals that have single unpaired electrons capable of forming covalent bonds. Now, let's put our newfound knowledge to work and develop a strategy to determine the number of hybridized orbitals on the central atom from a dot structure. It begins with the rule of thumb we covered earlier. Count the number of single bonds. This gives the number of s, p, and d orbitals that are combined into hybridized orbitals and is the central lesson of hybridization. It does not address what happens to the orbitals that are not part of the hybridization. That is covered in the next 2 steps. Count the number of lone pair electrons on the central atom. This gives the number of p orbitals that will have paired electrons. These orbitals will not be part of hybridization. And finally, count the number of multiple bonds that the central atom makes. This gives the number of p orbitals that have a single unpaired electron and will contribute to a multiple bond. These 2 do not participate in hybridization. A few examples, 4 to be exact, will help solidify the process. Beginning with the hybridization on silicon in SiCl4. Looking at the electronic configuration of silicon shows it to have 2 single unpaired electrons, and that suggests that it can form just 2 covalent bonds. It has 4 valence electrons, which is what it will need to form 4 covalent bonds. Hybridization is needed here so that those 4 electrons become single unpaired electrons in 4 even orbitals. Start the process of determining the number of basic orbitals that will be needed in hybridization by counting the number of single bonds on the central atom. There are 1, 2, 3, 4 single bonds. 4 basic orbitals, a single s and 3 p's, will need to be combined to form 4 sp3 hybridized orbitals. Before proceeding with the hybridization, we should finish our preliminary count. There are no lone pairs on the silicon. There will be no p orbitals with paired electrons. Silicon does not make any multiple bonds. There will be no p orbitals with a single unpaired electron. That leaves these 4 basic orbitals to be used to make the 4 sp3 equal energy orbitals. The 4 valence electrons of silicon can be added 1 per orbital. These 4 sp3 orbitals can form 4 sigma bonds, which is what is needed in this molecule. Example 2, and getting a bit more complicated. What is the hybridization of carbon in CO2? The electronic configuration of carbon is very similar to that of silicon. They both have 4 valence electrons. with a couple of p orbitals having a single unpaired electron. The electron configurations differ in the energy level of the orbitals. These are 2s and 2p orbitals, not the 3s and 3p of silicon. The procedure for determining hybridization has us count the number of single bonds that the central atom makes. 1, 2. Hybridization for 2 single bonds is sp, 1s and 1p. Now, it seems reasonable to ask why hybridization is needed when carbon has 2 p orbitals with single unpaired electrons that should be able to participate in covalent bonding. The answer is that we should finish the counting steps in the procedure first. We need a bit more information to tackle this. Are there any lone pair electrons on the carbon? No, there will be no p orbitals with paired electrons. Are there any multiple bonds? Yes, there are. 1, 2 multiple bonds. This means carbon will need 2 p orbitals that have single unpaired electrons. Now we're ready to answer the question of why carbon doesn't just use the 2 p orbitals with single unpaired electrons for covalent bonding. If it did so, it would not have 2 remaining p orbitals for the 2 multiple bonds it makes. Proceeding with the hybridization, there are 2 equal sp orbitals and 2 unchanged p orbitals. Adding in the 4 electrons, 1 per orbital, has the sp orbitals capable of making 2 single or sigma bonds, and the 2 p orbitals capable of making 2 pi bonds, multiple bonds. This arrangement allows carbon to form the bonding pattern found in CO2. Example 3 wants to know the hybridization on the phosphorus in phosphine, PH3. A look at the electronic configuration of the central atom phosphorus shows it to have 5 valence electrons, with each of the p orbitals having a single unpaired electron. And we begin with counting bonds. Taking off single bonds, we see that there is 1, 2, 3 bonds around the phosphorus. Hybridization will need 3 orbitals, sp2, the single s and 2 p's. This does raise the question as to why hybridization is needed here, since it looks like the electronic configuration of phosphorus shows that it can form 3 covalent bonds. Continuing with the count will show us why this is not so. Does phosphorus have any lone pair electrons? Yes, it does. It has 1, and phosphorus will need to have a p orbital with a pair of electrons. Phosphorus's electronic configuration does not have a p orbital with a pair of electrons. That is why this configuration cannot be used to form phosphine. Finishing off the counting, does phosphorus have any multiple bonds? No, it doesn't. On to hybridizing 1s and 2 p's to give 3 equal energy sp2 orbitals and 1 unchanged p orbital. Assign 3 of the 5 electrons, 1 each, to the 3 sp2 orbitals, and put the remaining 2 in the p orbital as paired electrons. This arrangement allows phosphorus to make 3 sigma bonds and have 1 lone pair. It is the hybridized electronic configuration that allows phosphorus to have the bonding pattern in phosphine. And finally, what is the hybridization of oxygen in water, H2O? Oxygen has an electronic configuration with 6 valence electrons. We determine the type of hybridization needed by the central atom oxygen by counting the number of single bonds. There are 1, 2 single bonds. 2 single bonds require the hybridization of 2 basic orbitals, sp hybridization, the single s orbital and 1 of the p orbitals. What about lone pair electrons? Yes, oxygen has 2 pairs. In this molecule, oxygen must have 2 p orbitals with paired electrons. Does oxygen make any multiple bonds? No, there will be no p orbitals with a single unpaired electron. Hybridization of an s and p orbital produces 2 sp orbitals. The remaining 2 p orbitals are unchanged. 2 of the 6 valence electrons go as single unpaired electrons in the sp orbital. The remaining 4 electrons go into the 2 unchanged p orbitals, 2 apiece. This configuration for oxygen can form 2 sigma bonds and has 2 sets of lone pair electrons. A quick note with the hybridization of the oxygen in water. It could be argued that the original electronic configuration is set up to make 2 sigma bonds and has 2 sets of paired electrons. What hybridization does here is let those 2 electrons in the s orbital be 2 electrons in the p orbital, a distinction that is well in advance of our current level of discussion. The topic of hybridization is a complex one, and one that the student should know what level of understanding is expected of them. Often it is just the count of single bonds to get the type of hybridization. A last topic, and one that many chemistry students are not exposed to at all, is called molecular orbitals, MO. We will cover at a level that just adds some familiarity to the topic. Earlier we saw how the 1s atomic orbital of a hydrogen atom and the 1s atomic orbital of another hydrogen atom can overlap to form H2, or sigma bond. The 2 1s orbitals are still there. They just have a region where they overlap. In the discussion of hybridized orbitals, we saw that the hybridization is a mathematical mixing of 2 or more orbitals in an atom. There is another type of mixing, and that is mathematically mixing of the orbitals involved in the bond. That is, mixing the bonding orbital in one atom with the bonding orbital in the other atom. The new mixed orbital is called a molecular orbital, and the atoms form a molecular sigma bond. In contrast to the orbital overlap we are used to seeing in covalent bonding, the molecular sigma bond is formed by the combination of atomic orbitals. Paired electrons range about the whole of the molecular orbital. Often, molecular orbitals are shown in comparison with the electronic configuration. Here we are starting out with one hydrogen atom, its electronic configuration, and another hydrogen atom with its electronic configuration. A mathematical recombination of the 2 1s orbitals generates the molecular sigma orbital. It is lower in energy than the 1s orbital and is therefore considered to be a bonding orbital. And like all orbitals we've come across, molecular orbitals can hold 2 electrons that have opposite spin. A final point needs to be made with molecular orbitals, and it is a matter that shares some of the mathematical oddity that is seen in hybridized orbitals. Calling up the visual representation of s and p orbitals, and the representation of those orbitals as sp2 hybridized orbitals, we note that the electrons, arrows here, were added to, for the lack of a better term, the fat part of the hybridized orbitals. Bringing up just one of those orbitals displays a lobe or a region that the mathematics say is where it is likely to find an electron, and a region where it is not so likely to find an electron. Something similar happens with the mathematics that give rise to the molecular sigma bonding region. It also produces an orbital or region where it is not favorable for bonding. It is an anti-bonding orbital and designated with an asterisk next to the sigma symbol. It is higher in energy than the molecular bonding orbital and the basic s orbital. Molecular orbitals are complicated, which is why they are at most briefly introduced as a topic or not mentioned at all. Recapping our lecture, we started out by defining the covalent bond. An orbital with one electron in one atom overlaps with an orbital with one electron in another atom. We call that a single or sigma bond. The bond is formed by an overlap of ends of the bonding orbitals. Double and triple bonds are a way to get extra electrons in an atom to fulfill the octet rule, and are called pi bonds. They involve p orbitals. There is no hybridization. They are not formed by overlap of ends of orbitals. They are formed by side-to-side overlap, and by that we mean the electrons are delocalized and migrate back and forth between lobes of different orbitals. as such double and triple bonds are parallel to the axis of the single bond. In a chemical formula, a multiple bond is drawn as lines, 2 parallel lines for the double bond, 3 parallel lines for the triple bond. Hybridized orbitals. This is a topic many students do not spend much time with. Know what is expected of you. Hybridized orbitals are atomic orbitals that are the mix of 2 or more basic types of atomic orbitals, with basic orbitals being s, p, or d orbitals. How does the student know which of the orbitals to mix together? Well, there is a rule of thumb that says count the number of single bonds on the central atom. That gives the number of basic atomic orbitals to combine. Keep in mind that these are valence electrons, and lowest energy orbitals are selected first. While this rule of thumb is generally sufficient understanding, for completion's sake, we also covered counting lone pair electrons on the central atom. That gives the number of p orbitals that are full. And counting the number of multiple bonds around the central atom, that gives the number of p orbitals with single unpaired electrons. A closer look at hybridization has sp hybridized orbitals as a mix of an s orbital with 1 p orbital. The absence of superscript numbers on the s and p in sp means that there is an implied 1 on each. Starting with a representation of basic s and p orbitals, 4 in all, sp hybridization has the s and 1 p orbital mathematically combining into 2 sp orbitals, which are mixed between the shapes of the basic orbitals. The larger lobe is where the single electron is drawn. It is also where the orbital overlaps in the formation of a covalent bond. The other 2 p orbitals are unchanged. To get sp2 orbitals, mix an s orbital with 2 p orbitals. To get 4 sp3 orbitals, mix an s orbital with all 3 p orbitals. To get sp3d hybridized orbital, mix the s, 3 p's, and a single d orbital. And then there is the more sophisticated molecular orbital, MO. These are formed by the combination of the atomic orbitals involved in the bond. That is combining 1 orbital from each atom. We saw that the combination can yield a bonding and an anti-bonding orbital. And that concludes our lecture. The best advice to go with this lecture is to know what is expected of you and study accordingly.